Right now, the sun is burning at 27 million degrees at its core. It has been doing this for 4.5 billion years, flooding space with enough energy every single second to power human civilization for 500,000 years, and it is just one star. There are 400 billion more in this galaxy alone, and 2 trillion galaxies beyond that, each filled with billions of their own nuclear furnaces. The universe is on fire. Everywhere you look, something is burning. Yet the space between those fires sits at nearly 455 degrees below 0 Fahrenheit. Step into the shadow of your own spacecraft, and the void will begin pulling heat from your body with nothing to stop it. The universe is full of fire and yet dominated by cold. The reason why will break your intuition forever. If you enjoy journeys that completely reshape how you see reality, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making content like this for you. Now, settle in and get yourself comfortable. Let's begin. Light a candle in a dark room. Within seconds, something invisible reaches your face. Warmth. Not light, not sound, but the physical sensation of heat crossing empty air and pressing against your skin. You do not need to touch the flame. You do not need to stand directly above it. You simply exist in the same room as that tiny fire, and the room gets warmer. This is the most basic lesson the universe ever taught the human species. Fire makes things hot. Not just the fire itself, not just the object that is burning, but the space around it. The air, the walls, the floor beneath your feet. Heat radiates outward from its source and fills whatever surrounds it. Every human being who has ever lived learned this lesson before they could speak. The warmth of a mother's body, the heat of the afternoon sun on bare skin, the glow of embers in a hearth that keeps an entire family alive through a winter night. Our deepest instinct about how the universe works can be summarized in 6 words. Hot things make everything around them hot. Now point that instinct at the sky. The sun burns at approximately 27 million degrees Fahrenheit at its core. Even its surface, the comparatively cool outer layer we can actually see, rages at around 10,000 degrees Fahrenheit. This is not a campfire. This is not a furnace. This is a thermonuclear explosion so immense that 1,300,000 Earths could fit inside it. Every single second, the sun converts roughly 4 million tons of its own matter into pure energy through nuclear fusion. Not 4 million tons per year, not per month, per second. The energy released in that single second equals approximately 3.8 times 10 to the 26th power watts. If you could somehow capture just 1 second of the sun's total energy output, you would have enough power to run every city, every factory, every vehicle, every device on Earth for roughly 500,000 years. And the sun is ordinary. It is a middle-aged, medium-sized, unremarkable yellow dwarf star. Astronomers classify it as spectral type G2V, which in stellar terms is the cosmic equivalent of a 4-door sedan. There is nothing special about it, nothing rare, nothing extraordinary. If you dropped our sun into a random location in the Milky Way, it would vanish into the crowd without a trace. The Milky Way contains somewhere between 100 billion and 400 billion other stars, many of them far larger, far hotter, and far more violent than our sun. Rigel, the blue supergiant anchoring the constellation Orion, burns at roughly 20,000 degrees on its surface and shines with the luminosity of approximately 120,000 suns. If you replaced our sun with Rigel, the inner planets would be vaporized. Earth would not melt. It would cease to exist as a solid object. Eta Carinae, one of the most massive and unstable stars known in our galaxy, radiates nearly 5 million times the energy of our sun. It is so violently luminous that it is tearing itself apart, shedding layers of superheated gas into surrounding space at millions of miles per hour. Eta Carinae is expected to explode as a supernova or hypernova in the astronomically near future, and when it does, the detonation will briefly outshine the entire Milky Way. These are not exotic outliers hidden in some forgotten corner of the galaxy. Massive hot stars are scattered throughout every spiral arm, every star-forming region, every dense cluster in the Milky Way. And between the giants, the ordinary stars burn quietly and relentlessly. Red dwarfs, the most common type of star in the galaxy, making up roughly 70% of all stellar objects, burn at lower temperatures than the Sun but still maintain surface temperatures of several thousand degrees. They burn for trillions of years. Trillions. Long after the Sun has exhausted its fuel and died, these small, patient furnaces will still be fusing hydrogen into helium, still radiating energy into the surrounding cosmos, and these are just the stars we can see in our own galaxy. Beyond the Milky Way, the observable universe contains approximately 2 trillion galaxies. 2 trillion. If you could somehow visit one galaxy per second, it would take you over 63,000 years to see them all. Each one of those galaxies is a city of stars. Some are small, containing a few billion stellar furnaces. Others are monstrous. IC1101, the largest known galaxy, spans roughly 6 million light-years across and contains over 100 trillion stars. 100 trillion nuclear explosions burning simultaneously in a single galactic structure. When you add up every star in every galaxy in the observable universe, you arrive at a number so large it requires scientific notation to even express. Roughly 10 to the 24th power individual stars. That number exceeds the total number of grains of sand on every beach on Earth. Each one of those stars is a nuclear furnace. Each one converts mass into energy through fusion reactions that produce temperatures measured in millions or billions of degrees. The total energy output of the observable universe in a single second is so staggering that no human analogy can contain it. You could stack every metaphor ever invented on top of each other and still fall short of the reality. But the fires of the universe are not limited to stars. Supernova explosions, the death throes of massive stars, release more energy in a few weeks than our Sun will produce in its entire 10 billion year lifetime. The shockwaves from these explosions heat surrounding gas clouds to millions of degrees, creating expanding shells of superheated plasma that glow in X-ray light for thousands of years. Neutron stars, the ultra-dense remnants left behind after certain supernovae, spin at hundreds of revolutions per second and emit beams of radiation so intense they can be detected from across the galaxy. Accretion disks around black holes heat in falling material to billions of degrees, producing jets of relativistic plasma that punch through intergalactic space for millions of light-years. Quasars, the most luminous objects in the universe, powered by supermassive black holes devouring matter at the centers of distant galaxies, shine with the brightness of entire galaxies, packed into a volume smaller than our solar system. The universe is burning. It has been burning for 13.8 billion years. It will continue burning for trillions more. Fire is everywhere. Energy is everywhere. Radiation saturates the cosmos. So here is the question that should keep you awake tonight. Why is space cold? Not just a little cold, not chilly, not brisk. The baseline temperature of the universe, measured in the vast emptiness between the stars, between the galaxies, between the great cosmic structures that stretch across billions of light years, is approximately 2.7 Kelvin. That is 2.7 degrees above absolute zero. Absolute zero, the theoretical floor of all temperature, the point at which molecular motion effectively stops, sits at minus 459.67 degrees Fahrenheit. The temperature of deep space hovers barely above that floor, minus 454.81 degrees Fahrenheit, minus 270.45 degrees Celsius. A cold so extreme that most gases become solid, a cold so deep that the very concept of warmth becomes alien. How is this possible? the universe contains more fire than the human mind can process. Trillions upon trillions of nuclear furnaces burning at millions of degrees, flooding space with light and energy and radiation every second of every day for billions of years. And the result of all that fire is a cosmos that sits just barely above the coldest temperature physics allows. If you told this to someone who had never looked through a telescope, who had never studied a single page of astronomy, they would call you insane. They would say you were lying. They would say that a universe full of fire cannot possibly be that cold. They would point at your campfire, at your stovetop, at the summer sun baking the pavement, and they would say, look, heat spreads, heat fills, heat warms everything it touches. Their instinct would scream at them that something is wrong with the math, something is broken in the logic. Enough fire should eventually warm anything. Given enough time and enough burning, the universe should be a furnace, not a freezer. That instinct is wrong. Profoundly, fundamentally, irreversibly wrong. And the reason it is wrong is one of the most unsettling truths in all of physics. It is a truth that has nothing to do with how much fire exists and everything to do with what is between the fires. Let us start with why your brain lies to you about heat. Everything you know about warmth, every intuition you possess about how hot and cold things behave, was built by evolution inside a very specific environment. You are a creature that lives at the bottom of an ocean. Not an ocean of water, but an ocean of air. Earth's atmosphere is a blanket of gas roughly 300 miles thick that wraps around the planet in every direction. You have never in your life experienced a moment outside of it. No human being in all of history, save for a few hundred astronauts sealed inside pressurized spacecraft, has ever directly felt what exists beyond this blanket. Every breath you take pulls in molecules of nitrogen, oxygen, argon, carbon dioxide, and trace amounts of other gases. These molecules surround you so completely, so continuously, so permanently, that you forget they exist. You walk through them. You breathe them. They press against your skin at 14.7 pounds per square inch, and you do not even notice. The air is invisible, odorless in its pure form, and constant. It is the most taken for granted substance in human existence, but those molecules are the reason you understand heat the way you do. They are the invisible infrastructure through which your entire experience of warmth has been constructed. When the sun shines on a patch of ground, the ground absorbs that energy and warms up. The warm ground then heats the air molecules directly above it through physical contact. Those warm molecules begin moving faster, bouncing into neighbouring molecules, transferring energy outward. The heated air rises because warm air is less dense, and cooler air rushes in below to replace it. This sets up a circulation pattern. Warm air climbs, cool air sinks. The atmosphere churns and mixes, carrying thermal energy from the ground upward into the sky. Over hours, the air temperature in an entire region equalizes. The afternoon feels warm not because sunlight is heating your skin directly, though it does that too, but because the air itself has become warm. You are surrounded by trillions of energized gas molecules bouncing against your body and transferring their kinetic energy to you. This is how you have always experienced heat. Through a medium, through stuff, through an ocean of matter that absorbs energy, carries it, distributes it, and shares it with everything it touches. Stand next to a bonfire and the air between you and the flames heats up. Open an oven door and a wave of hot air hits your face. Step outside on a summer day and the entire atmosphere wraps you in warmth that it collected from the sunlit ground below. In every case, the heat gets to you because there is something between the source and your body that can absorb thermal energy and pass it along. Your brain built its model of heat transfer from these experiences. It concluded, reasonably, that when something is hot, the area around it becomes hot too. That heat spreads outward from its source like ripples in a pond, filling whatever space is available. That given enough fire and enough time, any surrounding region should eventually warm up. This model works perfectly on Earth. It has worked for every human being, in every era of history. It guided our ancestors to build shelters, to insulate clothing, to cluster around fires in the winter, to seek shade in the summer. It shaped how we designed our homes, our vehicles, our cities. We insulate walls because we know heat escapes through them. We build chimneys because we know hot air rises. Every one of these technologies depends on the fact that Earth has an atmosphere, a medium, a substance that participates in the exchange of thermal energy. Strip that medium away, remove every molecule of gas, remove every particle of dust. Leave nothing but vacuum, true vacuum, the emptiness that fills the space between worlds, between stars, between galaxies. And the model that served humanity for 100,000 years becomes useless. This is exactly what space does. The universe between the stars is not filled with air. It is not filled with anything. The interstellar medium, the material that exists between star systems within a galaxy, has an average density of roughly 1 atom per cubic centimetre. To put that in perspective, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimetre. 25, followed by 18 zeros. The difference between Earth's atmosphere and the space between stars is not a matter of degree. It is a difference of 19 orders of magnitude. The vacuum of space is so empty that it makes the best laboratory vacuum chambers on Earth look like thick soup by comparison. And between galaxies, the emptiness is even more extreme. Intergalactic space drops to roughly 1 atom per cubic metre, not per cubic centimetre, per cubic metre. A volume the size of a large closet containing a single lonely atom of hydrogen, drifting through absolute nothingness with no neighbour for another cubic metre in any direction. If you could somehow stand in the middle of intergalactic space and reach out your hand, the nearest atom might be farther from your fingertips than the length of your entire body. This is emptiness on a scale that has no earthly equivalent. In this environment, 2 of the 3 ways that heat moves through the physical world simply stop working. Conduction, the transfer of heat through direct physical contact, requires matter touching matter. Molecules vibrate, collide with neighbouring molecules, and pass their energy along in a chain reaction that can move thermal energy through solid objects and dense fluids with remarkable efficiency. This is why a metal spoon gets hot when you leave it in boiling water. The water molecules slam against the metal atoms at the submerged end, energizing them. And that energy travels up the spoon molecule by molecule until the handle burns your fingers. This is why the sand at the beach scorches your bare feet on a hot day. The grains absorbed sunlight, heat it up, and when your skin makes contact, the energy transfers directly into your flesh. Conduction is immediate, intuitive, and powerful. On Earth, it is one of the primary ways heat moves from place to place. In space, there is nothing to slam against. No molecules touching other molecules, no chain of matter to conduct energy through, no solid surface connecting one hot region to a cold one. Conduction is dead. Convection, the transfer of heat through the movement of fluids, requires a gas or liquid that can circulate. Hot fluid rises, cool fluid sinks. Currents form and carry thermal energy across distances. This is how your home's heating system works. Warm air rises from a vent, circulates through the room, and gradually brings every corner to a comfortable temperature. In space, there is no fluid, no gas to rise, no liquid to sink, no medium to carry warmth from point A to point B. Convection is dead. That leaves only one mechanism: radiation. The emission of energy as electromagnetic waves, photons streaming outward from any object with a temperature above absolute zero. This is the only way heat travels through the vacuum of space. It is the only way the sun's energy reaches Earth. It is the only way starlight crosses the gulf between stellar systems. It is the only way warmth from a distant galaxy can ever make its presence known to anything beyond its own borders. Every photon that has ever warmed your skin on a sunny day travelled 93 million miles through perfect vacuum to get there, moving at the speed of light for roughly 8 minutes and 20 seconds before striking the atmosphere and eventually your face. During those 8 minutes and 20 seconds, that photon passed through a void containing almost nothing. It did not slow down. It did not lose energy to the vacuum. It did not warm the emptiness along its path. It simply travelled, unchanged and undiminished by the nothingness surrounding it, until it encountered something solid enough to absorb it. Radiation works. Energy absolutely crosses the vacuum. The sun proves this every day of your life. But here is the critical point that shatters your intuition about how the universe should feel. Radiation does not heat the vacuum itself. A photon leaving the sun does not warm the space it passes through. It does not deposit energy into the emptiness between the sun and the earth. It does not gradually raise the temperature of the void as it travels. The photon moves through vacuum at the speed of light, and the vacuum is completely transparent to it. The emptiness does not absorb the energy. It does not interact with the energy. The photon simply passes through as if the space between the source and the destination does not exist. The energy only becomes heat when it strikes something. A planet, a moon, a dust grain, the hull of a spacecraft, the fabric of an astronaut's suit. When a photon hits matter, it is absorbed, and the matter's temperature increases. But the void that the photon travelled through remains exactly as cold as it was before the photon entered it. 1 trillion photons can stream through a cubic meter of empty space every second, and the temperature of that cubic meter does not change by a single fraction of a degree. This is the crack in your intuition. This is where the human model of heat transfer falls apart. You assumed, because your entire life taught you to assume, that heat fills space. That fire warms the room. That enough burning should eventually warm everything. But fire only warms things that can absorb its energy. In a room full of air, that means every gas molecule in the room. On a planet with an atmosphere, that means the ground and the air above it and everything those touch. But in the vacuum of space, where there is nothing to absorb anything, the energy passes through without interaction. The fire burns. The photons fly. And the emptiness remains untouched. This is why the universe can be full of stars and still be cold. The stars are not failing to produce heat. They are producing staggering, incomprehensible amounts of energy. The sun alone outputs enough power every second to vaporize entire planets. But that power travels outward as radiation, and radiation only heats matter. In the vast stretches of emptiness between the stars, where matter is essentially absent, the energy simply passes through. It does not accumulate, it does not build up. It does not gradually warm the void the way a campfire gradually warms a room. The void has nothing to warm. Think about what this means at cosmic scale. The observable universe contains something like 10 to the 24th power stars, all burning, all radiating, all flooding space with photons. And those photons fill the universe, streaming in every direction at the speed of light, forming a crisscrossing web of electromagnetic energy so dense that every cubic centimetre of space is bathed in radiation from countless sources. The universe is literally glowing with energy. There is nowhere you can go in the cosmos where starlight is not reaching you from some direction, and none of it matters to the void. The baseline temperature of space remains 2.7 Kelvin. Not because there is no energy present, there is energy everywhere. Photons are everywhere. Radiation permeates every corner of the cosmos. But the emptiness between the sources and the destinations of that radiation does not participate in the exchange. It is a passive conduit, a transparent medium that lets energy pass without absorbing it. You could double the number of stars in the universe, triple them, multiply them by 1,000,000, and the temperature of the void between them would barely change. Because the void is not made of anything that can absorb heat. It is nothing, and nothing cannot get warm. This is what your brain refuses to accept. Every instinct screams that enough fire should heat anything. That if you surround a point in space with 1 trillion burning stars, that point should eventually become warm. But the point is vacuum. The point is emptiness. The point has no atoms to absorb photons, no molecules to vibrate, no matter to gain kinetic energy. The photons from those trillion stars pass straight through the point without stopping. each one continuing on its journey to some distant object that might, eventually, absorb it. The point remains at 2.7 Kelvin, the same temperature it has been since the cosmic microwave background radiation, the fading afterglow of the Big Bang, set the baseline temperature of the universe approximately 380,000 years after the cosmos began. That afterglow is all that remains. The cosmic microwave background is the oldest light in the universe, emitted when atoms first formed and space became transparent to radiation. Over 13.8 billion years of cosmic expansion, that ancient light has been stretched to microwave wavelengths, its energy diluted to the faintest whisper of warmth, 2.7 Kelvin. That is the temperature floor of the universe. Every point in the void between stars, between galaxies, between the great cosmic filaments that thread through the observable cosmos, sits at or near this temperature. It is the universe's default state, not because something made it cold, but because nothing ever made it warm. And this is the realization that reshapes how you see the cosmos. You look at the night sky and see fire, stars burning, galaxies glowing, nebulae lit from within by newborn suns. The universe looks warm. It looks alive with energy. It looks like a place where heat should be everywhere, where the sheer abundance of burning matter should have filled every corner of space with warmth over the course of 13.8 billion years. But the fire is an illusion of proximity. Each star heats the matter near it, the planets in its orbit, the dust in its vicinity, the gas clouds within its reach. Beyond that sphere of influence, the fire's energy passes through the void without effect. The warmth is local, the cold is universal, the islands of heat are tiny. The ocean of cold is everything else. You evolved at the bottom of an atmosphere that tricked you into believing heat works differently than it does. You grew up in a world where fire warms rooms, where sunlight heats air, where warmth spreads and fills and equalizes. None of that applies to the vacuum. In space, heat does not spread. It does not fill. It does not equalize. It travels in straight lines at the speed of light, and it only matters when it arrives somewhere that can absorb it. Between departure and arrival, the universe remains untouched. The photon does not care about the void it crosses. The void does not care about the photon. They share the same space and have no relationship whatsoever. This is why you can stand on a planet bathed in starlight and feel warm, while the space just above the atmosphere is lethally cold. This is why a comet passing close to the sun can develop a tail of vaporized ice on its sunlit face, while its shadowed side remains frozen solid. This is why an astronaut floating in low Earth orbit can experience searing heat on the sun-facing side of their suit and deep cold on the opposite side at the same time, in the same moment, separated by nothing more than the width of their own body. The deeper we go into how heat actually behaves in the void, the more disturbing the picture becomes. Because the failure of conduction and convection does not just leave space cold, it creates a universe where the difference between standing in sunlight and standing in shadow is not a matter of comfort. It is a matter of survival, and the physics behind that difference will fundamentally change how you understand the place you live in. Here is something most people never think about. The sunlight warming your face right now is 8 minutes old. It left the sun's surface as a burst of photons, crossed 93 million miles of vacuum at 186,000 miles per second, passed through the thin shell of Earth's atmosphere, and struck your skin. In that moment of contact, a packet of electromagnetic energy became heat, not before, not during the journey, only at the instant of arrival. For those 8 minutes and 20 seconds of travel, that photon existed as pure electromagnetic radiation, a ripple in the fabric of electric and magnetic fields, propagating through absolute nothingness at the maximum speed the universe allows. It had energy, it had frequency, it had wavelength, but it did not have temperature. It was not hot. It was not cold. It was energy in transit, belonging to nothing, warming nothing, until it made contact with something that could absorb it. This distinction between energy and heat is where the universe hides its most counterintuitive secret. We use the words interchangeably in everyday language. We say the sun sends heat to the earth. We say the fire gives off heat. But in physics, these statements are imprecise in ways that matter enormously when you leave the atmosphere behind. What the sun actually sends is radiation, electromagnetic energy, photons. These photons span a vast range of wavelengths, from high-energy ultraviolet and visible light to lower-energy infrared, and they all travel at the same speed through the vacuum, 186,000 miles per second. They carry energy encoded in their frequency. Higher frequency photons carry more energy. Lower frequency photons carry less. But none of them carry temperature. Temperature is not a property of radiation in transit. It is a property of matter, specifically the kinetic energy of atoms and molecules vibrating within a substance. A photon traveling through space has energy but no temperature because it is not made of atoms and it is not vibrating. It is a disturbance in an electromagnetic field, and it will remain nothing more than that until the moment it encounters matter. When photons are absorbed by matter, that matter converts the electromagnetic energy into thermal motion, the vibration of atoms and molecules that we measure as temperature. Heat is what happens after absorption. It is the end product, not the thing that travelled through space. The photon in transit is not heat. It is the potential for heat, waiting for a destination. A universe flooded with photons is not a universe flooded with heat. It is a universe flooded with the raw material from which heat can be made, but only where matter exists to receive it. This matters because it explains something that no amount of intuition can prepare you for. The space between the sun and the earth is flooded with solar radiation. Every square meter of the invisible sphere surrounding the sun at Earth's orbital distance receives approximately 1,361 watts of radiant energy. That is enough power to run a small space heater delivered continuously to every single square meter of that enormous sphere. The total energy passing through that spherical shell every second is the sun's full luminosity, roughly 3.85 times 10 to the 26th power watts, an almost incomprehensible river of energy flowing outward in every direction. And yet, the vacuum through which this river flows is not warm. The space at Earth's orbital distance from the sun, the space you would float through if you stepped outside the International Space Station without a suit, has no temperature of its own. It is not 250 degrees, it is not 70 degrees, it is not minus 400 degrees. It is nothing. The vacuum does not participate in the energy exchange. It is a transparent conduit with no thermal properties whatsoever. This is why the question, what is the temperature of space, requires a more careful answer than most people realize. When scientists say the temperature of space is 2.7 Kelvin, they are describing something specific. They are describing what the temperature of an object would eventually become if you placed it in deep space, far from any star, and let it reach thermal equilibrium with its surroundings. That object would slowly radiate away its own heat, losing energy as infrared photons streaming off its surface. As it cooled, it would absorb the only remaining source of energy available to it, the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the entire universe. Eventually, the object's emission rate and absorption rate would balance. It would stabilize at approximately 2.7 Kelvin. That is the equilibrium temperature of deep space. But it is the temperature an object reaches, not the temperature of the vacuum itself. The vacuum has no temperature. It is the emptiness in which temperatures happen to other things. Understanding this distinction unlocks everything that follows. Because what determines the temperature of any object in space is not where it is, but what it is doing, how much radiation it absorbs, how much it reflects, and how efficiently it radiates energy back out. Start with absorption. When a photon strikes the surface of an object, one of three things happens. The photon can be absorbed, meaning its energy transfers into the material, increasing the kinetic energy of the atoms in that material, raising its temperature. The photon can be reflected, bouncing off the surface without depositing any energy at all. Or the photon can be transmitted, passing through the material entirely, like visible light passing through a pane of glass. Every surface in the universe has its own specific ratio of these three behaviors, and that ratio determines everything about how hot or cold the object will get. Think about two objects sitting side by side in direct sunlight near Earth's orbit. One is painted matte black, the other is coated in polished silver. Both receive exactly the same amount of solar radiation, the same 1,361 watts per square meter, but the black object absorbs most of that energy. Its surface is designed to capture photons across a wide range of wavelengths, converting their energy into heat. The silver object reflects most of that energy. Its polished surface bounces photons away without absorbing them. The result is that the black object heats up dramatically while the silver object stays relatively cool, even though both sit in exactly the same location, exposed to exactly the same sunlight, same radiation, same distance from the sun, wildly different temperatures. In an atmosphere, air molecules would carry heat from the hotter object to the cooler one, eventually equalizing the difference. In space, there is no medium, no redistribution. Each object exists in its own private thermal universe, defined entirely by what it absorbs and what it emits. This is what engineers at NASA and ESA wrestle with every time they design a spacecraft. Thermal control in space is not about insulation the way it is on Earth. It is about managing the balance between absorption and emission. Every surface on a spacecraft is chosen for its specific optical properties. Radiator panels that need to dump excess heat into space are coated with materials that have high infrared emissivity, meaning they radiate energy efficiently. Surfaces that need to stay cool despite sunlight exposure are given low solar absorptivity coatings, often white or silver, that reflect incoming solar radiation while still being able to emit the spacecraft's own waste heat as infrared radiation. The ratio between how well a surface absorbs sunlight and how well it emits infrared radiation is one of the most critical design parameters in all of spacecraft engineering. Get it wrong and electronics fry. Get it wrong in the other direction and fuel lines freeze. The margin for error is razor thin, and it all comes down to the physics of absorption and emission in a vacuum where no other form of heat transfer exists. Now add distance. Radiation obeys the inverse square law, one of the most elegant and merciless rules in physics. When the sun radiates energy outward, that energy spreads across an ever-expanding sphere. At the distance of Mercury, roughly 1/3 of an astronomical unit from the sun, each square meter of that sphere receives approximately 9,100 watts. That is nearly 7 times the energy Earth receives. Mercury's sun-facing surface can reach over 800 degrees Fahrenheit. At Earth's distance, 1 astronomical unit, the flux drops to 1,361 watts per square meter. At Mars, roughly 1.5 astronomical units out, it falls to about 589 watts per square meter. At Jupiter, 5 astronomical units, the solar flux drops to roughly 50 watts per square meter. By the time you reach Pluto, nearly 40 astronomical units from the Sun, the solar energy hitting each square meter is approximately 1 watt. 1 single watt. The same Sun that blasts Mercury with 9,000 watts per square meter delivers barely enough energy to light a dim flashlight bulb by the time its radiation reaches the outer solar system. Double the distance, quarter the energy. Triple the distance, ninth the energy. The inverse square law is absolute. It is pure geometry. This is why the outer solar system is so cold. Not because the sun produces less energy. The sun's luminosity is constant whether Mercury or Pluto is watching. It is because the energy is diluted across so much more space that by the time it reaches the outer planets, there is almost nothing left per unit area. This is also why interstellar space is so brutally cold compared to the inner solar system. The nearest star to the Sun, Proxima Centauri, sits roughly 4.2 light-years away. That is approximately 25 trillion miles. At that distance, the sun's radiation has spread across a sphere so immense that the energy arriving per square meter is essentially zero by any practical measurement. The mighty sun, that blinding furnace that can burn your skin in minutes from 93 million miles away, becomes just another faint star in the sky from a distance of 4 light years. An object floating midway between the Sun and Proxima Centauri, roughly 2 light years from each, would receive radiation from both stars. But the combined flux would be so faint, so hopelessly diluted by the geometry of the inverse square law, that the object's equilibrium temperature would hover just barely above the cosmic microwave background, a few degrees above absolute zero. It would not matter that 2 nuclear furnaces existed on either side, each burning at millions of degrees at their cores. The distance dilutes their fire into irrelevance. 2 raging infernos, and the space between them is colder than anything you have ever experienced or could survive. But the inverse square law only determines how much radiation arrives at an object. What that object does with the radiation is equally important, and this brings us to the concept of thermal equilibrium, the central mechanism that governs temperature everywhere in the universe, where conduction and convection do not exist. Every object above absolute zero radiates energy. This is a fundamental law of physics, and there are no exceptions. Your body radiates infrared photons right now. The walls of the room you are in radiate. The ground beneath your feet radiates. A rock floating in deep space radiates. Everything with a temperature emits electromagnetic energy, and the amount of energy emitted increases sharply with temperature. The relationship is not linear, it is exponential. Double an object's absolute temperature, and it radiates 16 times as much energy. This extraordinary sensitivity means that, as an object heats up, it emits energy faster and faster, creating a natural brake on temperature increases. And as it cools down, it emits less and less energy, which means it loses heat more slowly the colder it gets. This is why objects in deep space never quite reach absolute zero. As they cool, their emission rate drops, and eventually even the faint trickle of energy from the cosmic microwave background is enough to balance the tiny amount they still radiate. They settle into an equilibrium just barely above the temperature floor of the universe. This process, thermal equilibrium through radiation, is the only temperature regulation mechanism that exists in the vacuum of space. There are no thermostat-controlled air ducts, no insulating blankets of gas, no convective currents to redistribute warmth. Just an object absorbing radiation from the sun and other sources and emitting its own infrared radiation into the void. When those 2 quantities balance, the temperature holds steady. When absorption exceeds emission, the object heats up. When emission exceeds absorption, it cools down. Every temperature you encounter in space, from the surface of Mercury to the hull of the International Space Station to the frozen crust of Pluto, is the result of this single equation: energy in versus energy out. Nothing more. Consider the Moon. It has no atmosphere, no air to circulate heat, no greenhouse gases to trap infrared radiation. Each point on the lunar surface reaches its own thermal equilibrium, based solely on how much sunlight it absorbs and how efficiently it radiates heat back into space. When the sun is directly overhead at the lunar equator, the surface absorbs roughly 1,300 watts per square meter of solar energy. The dark, rocky regolith absorbs this energy efficiently, heating the surface to approximately 260 degrees Fahrenheit, hot enough to boil water at sea level on Earth. The surface reaches this temperature because at 260 degrees Fahrenheit, the regolith's infrared emission rate matches the solar absorption rate. Equilibrium. The temperature holds, then the sun sets. On a world with no atmosphere, sunset is not a gradual cooling, it is a cliff. The moment the surface rotates into shadow, solar input drops to zero, but the surface continues radiating infrared energy into the void. With no incoming energy to replace what is being lost, the temperature plummets. Within hours, the surface falls to minus 280 degrees Fahrenheit. in the permanently shadowed craters near the moon's poles, where sunlight has not touched the ground for billions of years. NASA's Lunar Reconnaissance Orbiter has measured temperatures below -400 degrees Fahrenheit. These are among the coldest naturally occurring temperatures in the entire solar system, and they exist on a world that sits the same distance from the Sun as Earth. The difference between the moon's blazing daytime and its freezing night is not caused by something complicated. It is caused by the absence of something simple: air. Earth's atmosphere absorbs solar energy during the day, stores it in trillions of gas molecules, and releases it slowly at night. Wind patterns carry warmth from sunlit regions to shaded ones, from the equator toward the poles, from continental surfaces to offshore waters. The atmosphere traps infrared radiation escaping from the surface, absorbs it, re-emits it, and sends some of it back down. This process, known as the greenhouse effect, is not some exotic phenomenon. It is the most basic function of an atmosphere, and it is the single reason Earth is habitable. Without it, Earth's average surface temperature would be roughly 0 degrees Fahrenheit instead of the 59 degrees Fahrenheit we actually experience. The greenhouse effect raises our planet's temperature by nearly 60 degrees, and it does so entirely through the interaction between atmospheric gases and infrared radiation. This is why Earth's temperature only swings by a few dozen degrees between day and night in most places, while the moon swings by over 500 degrees across the same time span. The physics is identical. The sun's radiation is the same. The distance is the same. The only difference is a thin shell of gas roughly 60 miles thick at its densest, and that shell makes all the difference between a habitable world and a lifeless desert of thermal extremes. It is the difference between a planet where liquid water pools on the surface and one where water would either boil or freeze depending on which side faces the sun. This principle extends to every airless body in the solar system. Mercury, with virtually no atmosphere, experiences surface temperatures ranging from roughly 800 degrees Fahrenheit on its sunlit side to nearly -300 degrees Fahrenheit in shadow. The temperature swing on Mercury is over 1,000 degrees, the largest of any planet in the solar system, and it happens on the planet closest to the Sun. Mercury receives nearly 7 times the solar radiation that Earth does, and yet its dark side is colder than the surface of many moons in the outer solar system. The fire of the Sun heats only what it touches. Everything else freezes. Asteroids in the main belt between Mars and Jupiter experience similar behavior on a smaller scale. Sunlit surfaces heat up to modest temperatures based on their distance from the Sun and the darkness of their rocky surfaces. Shadowed sides plunge toward the baseline set by the cosmic microwave background. Even the asteroid's own body cannot equalize this difference the way Earth's atmosphere would, because rocks are poor conductors of heat and there is no air to circulate warmth from the bright side to the dark side. The result is objects that are simultaneously warm and freezing, divided by a boundary as sharp as a razor. Every airless rock in the solar system is a demonstration of what happens when radiation is the only game in town. Every one of them illustrates a truth so alien to everyday human experience that it requires conscious effort to accept, and every one of those demonstrations reinforces the same brutal lesson. Heat in space does not fill a region the way it fills a room. It illuminates one side and abandons the other. It is directional, specific, and ruthlessly local. A surface facing the Sun receives energy. A surface facing away receives nothing except the faint glow of distant stars and the ancient whisper of the cosmic microwave background. The transition between sunlight and shadow is not a gradient. It is a wall. On one side, temperatures that can melt lead. On the other side, temperatures that can freeze nitrogen solid. This directionality is what separates the physics of heat in space from everything your instinct tells you. On Earth, heat behaves like a gas. It expands to fill available space. It diffuses through air. It reaches around corners and under doors and through cracks. On Earth, being near a hot object means the whole area becomes warm, because air molecules carry the energy everywhere. In space, heat behaves like a beam of light, because it is light. Infrared radiation travels in straight lines. It does not bend around obstacles. It does not seep into shadows. It does not accumulate in empty regions. It travels from source to destination, and wherever it does not directly strike, the cold remains absolute. This is also why objects in space can only lose heat through radiation. On Earth, if something is too hot, you can blow cool air across it, you can dunk it in water, you can press it against a cold metal surface. Each of these techniques uses a different mechanism, convection, convection again, and conduction, to pull thermal energy away from the object. In space, none of these options exist. There is nothing to blow, nothing to dunk into, nothing cold to press against except other parts of your own spacecraft, which only moves the problem around rather than solving it. The only way for an overheating spacecraft to shed excess warmth is to radiate it away as infrared photons, one by one, streaming off the surface and into the void at the speed of light. This is painfully slow compared to convective cooling. A fan can cool an overheating laptop in seconds. Radiative cooling of the same electronics in vacuum would take far longer, because radiation is inherently less efficient than forcing cool fluid across a hot surface. This is why the International Space Station has enormous radiator panels extending out from its main truss, panels whose sole purpose is to glow in the infrared, dumping the station's waste heat into the void photon by photon. These radiators use ammonia coolant loops to collect waste heat from the station's modules and transport it to the panel surfaces, where it is radiated away. Without those radiators, the electronics, life support systems, and 6 or 7 human occupants aboard the station would cook in their own waste heat within hours. Keeping the station cool is actually a harder engineering problem than keeping it warm. People expect space to be cold and assume heating is the challenge. In reality, for a crewed spacecraft generating significant internal power, the challenge is getting rid of heat when the only exit is radiation. The same problem faces every piece of technology humans have ever sent into space. Rovers on Mars must balance absorption and emission to survive the Martian night, when temperatures drop to -100 degrees Fahrenheit and the thin Martian atmosphere provides almost no thermal insulation. The Voyager probes, now in interstellar space more than 15 billion miles from the Sun, receive so little solar radiation that their equilibrium temperature would drop near absolute zero, if not for the small amount of waste heat generated by their decaying plutonium power sources. Those plutonium generators are slowly dying. Within the next decade or two, they will no longer produce enough power to keep the probe's instruments warm enough to function, and Voyager 1 and Voyager 2 will go silent, drifting through the freezing void between stars with no fire left to sustain them. The James Webb Space Telescope, designed to observe the faintest infrared light in the universe, must keep its instruments cooled to roughly -370 degrees Fahrenheit. And it accomplishes this by using a massive sunshield the size of a tennis court that blocks solar radiation from reaching the telescope, while the shadowed side radiates residual heat into the cosmos. The sunlit side of that shield reaches approximately 185 degrees Fahrenheit. The shadowed side drops to -394 degrees Fahrenheit. The difference is nearly 600 degrees, occurring across a structure you could walk across in a few seconds. On one side, hotter than the Sahara, on the other, colder than the surface of Pluto, separated by nothing but a few thin layers of specially coated material. This is the universe radiation built, a cosmos where the fire of stars is real but confined, where energy travels endlessly through transparent emptiness without warming it, where the temperature of any object depends not on where it is in some absolute sense, but on the fragile balance between what it absorbs and what it emits. An object in Earth orbit can be simultaneously broiling and freezing depending on which direction it faces. A moon can have temperatures hot enough to boil water and cold enough to freeze carbon dioxide on the same day, separated by nothing more than the angle of incoming sunlight. A spacecraft can carry astronauts at comfortable room temperature through a void that would kill them in seconds, all because the engineers understood that in space, You do not manage temperature by controlling the air. You manage it by controlling the photons. Radiation explains why heat reaches objects across space, but it also creates a reality far more savage than any physics textbook can convey. Because understanding that heat in space is directional and local leads to a single, unavoidable conclusion. When you step into the shadow of your own spacecraft and leave the sunlight behind, you are not stepping into shade the way you would step under a tree on a summer afternoon. You are stepping out of the fire and into the freezing vacuum of a universe that has no warmth to offer you. The tree's shade on Earth is cooler because the air is slightly less warm. The shadow in space is colder because there is no air at all. And the only thing standing between you and temperatures approaching absolute zero is the residual heat in your own body and whatever technology you brought with you to manage it. The difference between standing in sunlight and standing in shadow in the vacuum of space is not a matter of comfort. It is the distance between survival and death. And the places where that difference plays out most visibly are the airless worlds of our own solar system, where the sun's radiation creates conditions so extreme they would break every assumption you have ever held about how heat is supposed to work. Here is a detail that changes everything about how you picture an astronaut floating in space. The biggest thermal threat during a spacewalk is not freezing, it is overheating. Your body is a furnace. Every second you are alive, metabolic reactions in your cells generate heat, roughly 100 watts at rest, and considerably more during physical exertion. On Earth, your body sheds this excess heat effortlessly. Warm blood flows to your skin. Sweat evaporates into the air, carrying thermal energy with it. The breeze pulls heat away from your exposed surfaces. Your body is a finely tuned cooling machine, evolved over millions of years to dump waste heat into an atmosphere that obligingly carries it away. Now, remove the atmosphere. Seal that 100-watt furnace inside an airtight suit surrounded by vacuum. Suddenly, the only way your body can lose heat is through the suit's outer surface radiating infrared photons into space. Radiative cooling is slow. It is nowhere near fast enough to keep up with a human body working hard in a pressurized suit. Without active intervention, an astronaut on a spacewalk would overheat within minutes, drenched in sweat that has nowhere to evaporate, trapped inside a bubble of rising body heat that cannot escape. This is why every EVA spacesuit ever built includes a liquid cooling garment worn directly against the astronaut's skin. Roughly 300 feet of narrow tubing is woven into a tight-fitting undergarment that covers the torso and limbs. Chilled water circulates through these tubes, absorbing heat directly from the astronaut's body through conduction, the one form of heat transfer that still works when you have physical contact between materials. The warmed water is pumped to a sublimator or heat exchanger in the suit's backpack, where the heat is transferred to water that is allowed to sublimate, transforming from ice to vapor and carrying the thermal energy away into space. It is an extraordinary piece of engineering, a miniature cooling system designed to solve a problem that would never exist on Earth. In an environment where the external temperature can swing hundreds of degrees depending on sun angle, the most dangerous thermal threat to a human being is the heat they generate themselves. The fingertips tell the opposite story. Hands are the body's thermal extremities. Blood flow to the fingers is limited by their small volume and distance from the core. In a spacesuit, the gloves are the thinnest part of the thermal protection system because astronauts need dexterity to operate tools and grip handrails. Every spacewalking astronaut reports the same experience. Their fingers get painfully cold, especially when gripping metal tools or handrails that have been sitting in shadow. Metal conducts heat away from flesh rapidly, and in the absence of surrounding warm air to buffer the temperature difference, the astronauts' fingers lose heat directly to whatever they touch. NASA's current EVA gloves include small heaters in the fingertips to combat this. Even so, astronauts frequently report numbness, pain, and in some cases, fingernail damage from the cold exposure during extended spacewalks. This is what the physics of space feels like at the human scale. Your torso overheats, your fingers freeze. Both things happen simultaneously, inside the same suit, on the same body. The suit's thermal management system fights a war on two fronts, pumping heat away from the core while trying to keep the extremities warm enough to function. It is a war that could not exist on Earth, where the atmosphere would equalize these differences in seconds. In space, each part of your body negotiates its own separate thermal fate, mediated entirely by radiation, conduction through direct contact, and whatever engineered systems stand between you and the void. But the experience becomes even stranger when you consider what surrounds the astronaut beyond the suit. The International Space Station orbits Earth at roughly 250 miles altitude, completing a full circuit every 90 minutes. During that orbit, the station passes from full sunlight into Earth's shadow and back again roughly every 45 minutes. When the station is in sunlight, the external surfaces facing the sun reach approximately 250 degrees Fahrenheit. When the station crosses into Earth's shadow, those same surfaces plunge to approximately minus 250 degrees Fahrenheit within minutes. A temperature swing of 500 degrees, happening every 45 minutes, 16 times per day, relentlessly, endlessly, for as long as the station remains in orbit. There is no gradual transition. The station does not slowly cool and slowly warm the way a building cools after sunset on Earth. It snaps from one extreme to the other because there is no atmosphere to buffer the change, no thermal mass of air to smooth the oscillation. The only thing that prevents the interior from experiencing these wild swings is the station's active thermal control system, a complex network of ammonia coolant loops and radiator panels that work continuously to keep the interior stable at a comfortable 70 degrees Fahrenheit, while the exterior lurches between extremes that would kill an unprotected human. In either direction, an astronaut performing a spacewalk during an orbital sunrise experiences something no earthbound human ever has. One moment, they are in shadow, surrounded by the blackness of space and the cold glow of stars, the station's exterior surfaces cold enough to freeze exposed skin on contact in seconds. Then the sun rises over Earth's curved horizon, and within a heartbeat, the suit's sun-facing side begins absorbing intense solar radiation. There is no dawn, no gradual brightening, no slow warming of the air over the course of an hour. The transition from darkness to full solar illumination takes seconds, and it is a hard line between two fundamentally different thermal realities, separated by nothing more than the geometry of light and shadow in a vacuum. The astronaut's visor, coated with a thin layer of gold to reflect infrared and ultraviolet radiation, suddenly becomes the only thing standing between their eyes and raw, unfiltered sunlight carrying over 1,300 watts per square meter of radiant energy. These experiences reveal something essential about the nature of heat in the cosmos. The extremes astronauts face are not anomalies. They are the default condition of the universe. Earth, with its thick atmosphere and convective weather systems and thermal buffering oceans, is the anomaly. The overwhelming majority of the universe operates under the same rules that govern a spacewalk: radiation only. No conduction except where matter touches matter. No convection at all. The astronaut floating outside the station is experiencing the universe as it actually is, stripped of the atmospheric illusion that makes heat feel gentle and pervasive and evenly distributed. And the universe, as it actually is, has a temperature floor. The cosmic microwave background radiation is not merely a scientific curiosity mentioned in physics textbooks. It is the single most important feature of the thermal universe, the baseline upon which all other temperatures are built. To understand why the spaces between stars and between galaxies are as cold as they are, you need to understand where this radiation came from, what it is, and why it sets the minimum temperature of nearly everything in the cosmos. Approximately 380,000 years after the Big Bang, the universe underwent a transformation so abrupt and so complete that it redefined the nature of light itself. Before that moment, the cosmos was a seething fog of plasma, a soup of free electrons and protons, so dense and so hot that photons could not travel more than a tiny distance before being absorbed and re-emitted by the surrounding charged particles. Light was trapped. The universe was opaque. No photon could travel freely through space because every direction was blocked by a wall of ionized matter. The entire cosmos glowed white-hot, hotter than the surface of any star that exists today. And none of that light could escape to travel across the distances that would later separate galaxies. Then the temperature dropped below roughly 3000 Kelvin, and something extraordinary happened. Electrons slowed down enough to be captured by protons, forming neutral hydrogen atoms for the first time. In an instant, the universe went from opaque to transparent. The charged particles that had been scattering photons were gone, replaced by neutral atoms that let light pass through unimpeded. The photons that had been trapped for hundreds of thousands of years were suddenly free. They streamed outward in every direction, carrying the thermal signature of the universe as it existed at that precise moment. Those photons had been travelling ever since. Over 13.8 billion years of cosmic expansion, the universe has stretched enormously. Space itself has expanded, and the wavelengths of those ancient photons have expanded with it. What began as white-hot visible and ultraviolet light has been stretched into microwave radiation, its energy diluted by the expansion of space from a searing 3000 Kelvin to a faint 2.725 Kelvin. But the photons are still here. They fill the entire universe. Every cubic centimetre of space, no matter how remote, no matter how far from any star or galaxy, is bathed in this ancient radiation. It comes from every direction equally, a uniform glow left over from the moment the universe first became transparent. This radiation was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey. They had built a highly sensitive microwave antenna and kept detecting a persistent hiss of low-level static that they could not eliminate. The noise appeared at the same intensity from every point in the sky, day and night, summer and winter, regardless of where the antenna pointed. Penzias and Wilson spent months trying to track down the source. They checked the electronics. They rebuilt connections. They even cleaned pigeon droppings from inside the antenna horn. Nothing worked. The noise persisted. Meanwhile, less than 40 miles away at Princeton University, a team of physicists led by Robert Dicke had predicted that if the Big Bang theory was correct, the afterglow of the initial fireball should still be detectable as faint microwave radiation filling the entire universe. They were building their own antenna to search for it. When Penzias and Wilson learned about the Princeton prediction through a mutual contact, the pieces fell into place. The inexplicable static was the afterglow of creation itself. The photons Penzias and Wilson were detecting had been travelling through the universe for over 13 billion years, the oldest light in existence. That discovery earned them the Nobel Prize in Physics in 1978, and it remains one of the most important observations in the history of science. It confirmed the Big Bang theory, established the thermal history of the cosmos, and revealed that the entire observable universe is bathed in a faint, uniform glow of ancient radiation that defines the temperature baseline of everything. The cosmic microwave background sets the temperature floor of the universe because it is everywhere. An object in deep space, far from any star, far from any galaxy, floating in the emptiest void between the great cosmic filaments, will eventually radiate away all of its internal heat until it reaches thermal equilibrium with the only radiation source available to it, the cosmic microwave background. At that point, the object stabilizes at approximately 2.7 Kelvin. It cannot cool below this temperature naturally because the background radiation constantly supplies a tiny trickle of energy that balances the object's own feeble emissions. The CMB is the universe's thermostat, not in the sense that it regulates temperature actively, but in the sense that it defines the coldest anything can naturally become without extraordinary circumstances. Those extraordinary circumstances do exist. and they produce the coldest known place in the entire universe. 5,000 light-years from Earth, in the direction of the southern constellation Centaurus, a dying star is performing an act of cosmic refrigeration, so extreme that it has chilled its surroundings below the temperature of the cosmic microwave background itself. The Boomerang Nebula, a pre-planetary nebula surrounding a star in the very final stages of its life, has a temperature of approximately 1 Kelvin, 1 single degree above absolute zero, minus 458 degrees Fahrenheit. That is colder than the cosmic microwave background. It is colder than the void between galaxies. It is the coldest naturally occurring temperature ever measured anywhere in the observable universe. The mechanism is adiabatic expansion, the same principle that makes compressed gas feel cold when released from an aerosol can. When gas expands rapidly into a larger volume, it does work on its surroundings, and that work costs energy. The energy comes from the gas's own thermal motion, which means the gas cools as it expands. In the Boomerang Nebula, the central star has been ejecting material at extraordinary rates, roughly 100 times faster than typical dying stars, for approximately 1,500 years. The gas rushes outward at roughly 164 kilometers per second, over 300,000 miles per hour, expanding into the surrounding vacuum so rapidly that it cools below the cosmic microwave background temperature. The expanding gas is essentially refrigerating itself, spending its own thermal energy to push outward, cooling to a temperature that the surrounding universe cannot match. The result is bizarre. The Boomerang Nebula actually absorbs the cosmic microwave background radiation rather than emitting against it. Astronomers detected this in 1995 by observing that the nebula appeared as a shadow against the microwave background, colder than the radiation passing through it. It is the only known natural object in the universe with this property. Everything else either emits radiation at a temperature above the CMB or sits in equilibrium with it. The Boomerang Nebula is an anomaly, a cosmic refrigerator powered by the death of a star, and it offers a profound lesson. Reaching temperatures below 2.7 Kelvin requires actively spending energy, fighting against the background radiation that fills all of space. The universe does not want to be that cold. The CMB prevents it. Only extreme, violent, short-lived processes can push temperatures below the floor, and when the process ends, the region will warm back up to the baseline. The cold of the Boomerang Nebula is temporary. The cold of the cosmic microwave background is permanent. This permanence defines the thermal landscape of the universe at every scale. Within galaxies, stars heat the matter around them. Dust grains absorb starlight and re-emit infrared radiation. Gas clouds warm and cool in response to the radiation fields that bathe them. Nebulae glow. Planetary surfaces warm in sunlight and cool in shadow. All of this thermal activity happens within the island of matter that constitutes a galaxy. Between those islands, in the vast reaches of intergalactic space, the story is entirely different. Intergalactic space is the closest thing the universe has to true emptiness. The density of matter between galaxies drops to roughly 1 atom per cubic meter. In some regions it falls even lower. There are no dust grains to absorb radiation and re-emit it. There are no gas clouds dense enough to trap heat. There are no surfaces for photons to strike. Starlight from distant galaxies streams through these regions at the speed of light and continues onward for millions or billions of years without interacting with anything at all. The radiation passes through, and the void remains at its baseline, 2.7 Kelvin, unchanged by the countless photons traversing it every second. If you could somehow hover in the middle of intergalactic space, between two galaxy clusters separated by hundreds of millions of light-years, you would be surrounded by photons. The cosmic microwave background would bathe you from every direction. Distant starlight from billions of galaxies would pass through your location continuously. You would be immersed in radiation, and yet the effective temperature of your surroundings would be just a few degrees above absolute zero. The radiation is there, the warmth is not, because warmth requires absorption, and absorption requires matter, and matter is the one thing intergalactic space almost entirely lacks. Within the great cosmic voids, the emptiest regions of the universe, the isolation is even more extreme. These voids are spherical regions hundreds of millions of light-years across, where galaxy density drops to a fraction of the cosmic average. Some of the largest known voids contain almost no galaxies at all. Inside these immense bubbles, the radiation environment is dominated almost entirely by the cosmic microwave background. Starlight from the distant walls of the void, where galaxies cluster along cosmic filaments, is so faint by the time it reaches the center of the void that it contributes virtually nothing to the local energy budget. An object placed at the center of a major cosmic void would cool to essentially 2.7 Kelvin and remain there, warmed by nothing but the ancient afterglow of creation. This creates a thermal map of the universe that mirrors its matter distribution with eerie precision. Wherever matter concentrates, temperatures rise. The cores of stars reach millions of degrees. Accretion disks around black holes blaze at billions of degrees. Even the diffuse gas within galaxy clusters, heated by gravitational compression, reaches tens of millions of degrees. But step outside these concentrations, into the empty space between the clusters, between the filaments, between the walls of the cosmic web, and the temperature drops to the background level almost immediately. There is no gradual cooling gradient stretching across the cosmos. There is no gentle transition from warm to cold like the temperature drop you feel walking from a heated building into a winter night. The transition is as sharp as the boundary between matter and vacuum. A galaxy cluster can contain gas at 100 million degrees, superheated by gravitational compression and shock waves from colliding galaxies, and the space just beyond its boundary sits at a few degrees above absolute zero. The contrast is not a gentle slope, it is a cliff, a wall. Heat exists where matter exists, cold exists everywhere else. The boundary is the presence or absence of stuff, and in a universe that is overwhelmingly empty, the cold wins by default. The warm regions are tiny candles. The cold regions are an ocean stretching in every direction to the edge of the observable cosmos and beyond. This sharpness extends all the way down to the smallest scales. Consider a single dust grain floating in interstellar space within our galaxy. A tiny mote of silicate or carbon, perhaps a micrometer across, smaller than a red blood cell, drifting through the void between star systems. This grain absorbs photons from distant stars, the integrated starlight of the entire galaxy bathing it from all directions in a faint, diffuse glow. Each photon that strikes the grain deposits a tiny amount of energy, warming it slightly above the cosmic background temperature. The grain heats up until its own infrared emission balances its absorption, reaching a thermal equilibrium, somewhere between roughly 10 and 20 Kelvin, depending on its distance from the nearest star and the density of the interstellar radiation field. 10 to 20 Kelvin. Still incredibly cold by human standards, hundreds of degrees below freezing, but warm compared to the 2.7 Kelvin baseline of the void. That grain is warmer than the background, but move just a few meters away from the grain, into the vacuum beside it, and the temperature is back to the baseline. The grain's thermal influence extends no further than its own surface. It cannot warm the vacuum around it. It can only radiate infrared photons that will travel outward until they strike another grain, or a gas molecule, or a surface somewhere, perhaps light years away. The vacuum between the grain and its eventual photon destination is completely unaffected by the exchange. This is heat transfer at its most minimal. One tiny mote, warmed by starlight, glowing faintly in the infrared, surrounded on all sides by space that does not care that it exists. Now multiply that by every dust grain, every gas atom, every pebble and boulder and moon and planet and star in the universe. Each one is an island. Each one absorbs radiation, heats up to its own equilibrium temperature, and re-emits infrared photons into the void. The universe is filled with these tiny transactions, countless objects absorbing and re-emitting, passing energy from source to destination across the emptiness. But the emptiness itself never participates. It never warms up, It never accumulates heat. It serves only as the transparent medium through which photons travel from one island of matter to the next. Some of these islands are enormous. Stars heat entire planetary systems. Galaxy clusters contain hot gas that fills millions of cubic light years, but even the largest structures are tiny compared to the voids between them. The hot gas inside a galaxy cluster might span 10 million light years. The void on the other side of the filament might span 300 million light years. The ratio is staggering. For every unit of space that contains hot matter, there are dozens or hundreds of units that contain nothing but the cosmic microwave background, and the re-emission process itself is not free. Every time a photon is absorbed and re-emitted, the physics of thermal radiation applies. Objects emit most strongly at wavelengths determined by their temperature. Hot objects emit short wavelength photons, visible light, ultraviolet, even X-rays. Cooler objects emit longer wavelength photons, infrared, microwaves. When starlight strikes a dust grain, and the grain re-emits the energy as infrared radiation, the photons that leave are lower energy, longer wavelength, less concentrated than the photons that arrived. The energy is conserved but degraded. Each re-emission step shifts the radiation toward lower frequencies and longer wavelengths. Over cosmic timescales, through countless absorption and re-emission cycles, the universe's energy is slowly being diluted, stretched, degraded, moving from concentrated high-energy sources toward the diffuse low-energy background. The stars burn hot, the dust glows warm, the gas shimmers faintly, and the background radiation grows ever colder as the universe expands and stretches its ancient photons to longer and longer wavelengths. This is the process by which the universe slowly dies thermally. Not in a dramatic explosion or collapse, but in the gradual, relentless degradation of energy from useful, concentrated forms into useless, diffuse forms. Physicists call this increase in entropy, and it is one of the most fundamental and inescapable truths in all of physics. The second law of thermodynamics guarantees it. The universe is not running out of energy. Energy is conserved. It cannot be created or destroyed, but it is running out of useful energy. Energy concentrated enough to power processes, to heat objects, to drive chemistry and biology and thought. Every time a star shines and its light is absorbed by dust and re-emitted as infrared, the universe moves one step closer to a state where all energy is evenly distributed at the lowest possible temperature, and nothing interesting can ever happen again. Every nuclear reaction in every stellar core, every photon absorbed and re-emitted by every grain of dust, every metabolic process in every living organism pushes the cosmos incrementally toward this final state. The fire burns, and in burning, brings the universe one step closer to a future in which no fire can burn at all. But that final state is unimaginably far in the future, trillions upon trillions of years away, so distant that it makes the current age of the universe look like the first tick of a cosmic clock. For now, the universe is alive with thermal contrast. Stars blaze at millions of degrees. Planets warm in the glow of their parent suns. Gas clouds glow with the energy of newborn stellar systems. Nebulae shimmer with the recycled light of dying stars. And between all of these, stretching across distances that dwarf every structure, filling the vast majority of the cosmic volume, the void persists at its ancient baseline. Patient, unchanging, 2.7 Kelvin. The coldest and most enduring feature of the cosmos, the fire rages in its tiny pockets. The cold stretches between them, unbroken and indifferent, and the gulf between the two defines the physical character of the universe we inhabit. The universe is not a warm place with pockets of cold. It is a cold place with pockets of warm. The darkness between the stars is the rule. The light of the stars is the exception. And the exception is losing, slowly, imperceptibly, as entropy marches forward and the fire gradually spends itself across the long, cold future of an expanding cosmos. What this means for how we should see ourselves and for how we should feel about the fragile bubble of warmth we call home is something that only becomes clear when you step back far enough to see the full picture. And the full picture is not comforting. Look up. On a clear night, away from city lights, the sky appears full. Stars crowd every inch of darkness. The Milky Way stretches from horizon to horizon, a river of light so dense it seems to paint the blackness white. You can see thousands of stars with the naked eye, and behind each visible star lie millions more, too faint for human eyes but burning just as fiercely. Galaxies hide among the stars, each one a smudge of ancient light containing billions of its own nuclear furnaces. The sky looks rich, it looks abundant. It looks warm with the glow of a universe that has been burning for 13.8 billion years. Every culture in human history has looked up at this sky and felt something. Awe, wonder, connection. A sense that the cosmos is alive with light and fire and energy. That the darkness between the stars is merely a backdrop, a curtain behind which even more fire burns. It is a lie. One of the most convincing lies the universe has ever told. Your eyes cannot show you what is actually there, because what is actually there is overwhelmingly nothing. The light you see represents the tiny fraction of the cosmos that happens to contain matter, the rare islands of substance scattered through an ocean of emptiness, so vast that the islands are statistically irrelevant. If you could somehow color-code the universe, painting every region with matter in red and every region without it in blue, the entire observable cosmos would appear as a solid, unbroken wall of blue with a faint red mist barely visible on its surface. The galaxies you admire, the stars you navigate by, the blazing quasars and spinning pulsars and colliding neutron stars that make the universe seem dramatic and alive, all of them together occupy less than 1/billionth of the total volume. The rest is void. The rest is cold. The rest is the cosmic microwave background whispering at 2.7 Kelvin in every direction. The faint, ancient hum of a universe that was once on fire but has been cooling for almost 14 billion years. The night sky is not a portrait of abundance. It is a portrait of emptiness, with a few scattered sparks that your brain, desperate for pattern and meaning, inflates into a vision of cosmic warmth that does not exist. This is the truth that every single moment of this story has been building toward. Not a physics lesson, not a trivia fact. Number 5. A fundamental correction to the way human beings imagine the cosmos. We picture the universe as a place where things happen. Stars burn, galaxies spin, planets orbit, life evolves. These things are real, but they are exceptions. They are statistical outliers in a cosmos whose default state is emptiness, silence, and cold. The overwhelming majority of the universe, measured by volume, has never been warm, has never been lit, has never been touched by the energy of a nearby star. It has sat at the cosmic baseline since the universe became transparent, and it will remain there long after the last star has burned out, and the stars will burn out. This is not speculation. It is the inevitable consequence of the second law of thermodynamics, the most merciless law in all of physics. Stars are not eternal. They are machines that convert hydrogen into helium through nuclear fusion, and they have a finite fuel supply. Our Sun has approximately 5 billion years of hydrogen remaining. When it exhausts that supply, it will swell into a red giant, engulfing Mercury and Venus, scorching the Earth into a lifeless cinder, and eventually shedding its outer layers to leave behind a white dwarf, a tiny cooling ember the size of Earth but with the mass of a star. That ember will glow for billions of years, radiating its residual heat into the void, growing dimmer and cooler with each passing eon, until it fades below detection. A black dwarf, a cold, dark corpse of a star that once lit an entire solar system. Every star in the universe faces this same fate, differing only in timescale and drama. The massive ones, the blue giants and supergiants that burn with the brilliance of a million suns, exhaust their fuel in just a few million years and die in cataclysmic supernova explosions that briefly outshine entire galaxies before fading to darkness. The medium ones, like our Sun, last roughly 10 billion years before swelling into red giants and collapsing into white dwarfs. The smallest ones, the red dwarfs that make up roughly 70% of all the stars in the Milky Way, burn so slowly and so efficiently that they can last for trillions of years, 100 times longer than the current age of the universe. These tiny, patient furnaces will be the last stars shining in a cosmos that has long since gone dark around them. In 10 trillion years, when the sun is a cold, invisible cinder, when galaxies have consumed or expelled their gas, when the great nebulae have dissipated and no new stellar nurseries light up the sky, the red dwarfs will still be there. Faint, dim, barely glowing, the last embers of a fire that once lit the universe. But even they will eventually exhaust their hydrogen. Even they will cool, dim, and die. Star formation itself will cease entirely in approximately 100 trillion years when the raw material for making stars is finally gone. After that, no new stars will ignite. The universe will enter what physicists call the degenerate era, a vast, dark epoch dominated by stellar remnants, white dwarfs cooling toward invisibility, neutron stars spinning down to silence, and black holes drifting through expanding space with no new fire to replace what has been lost. The black holes will be the last to go, the most massive ones, the supermassive giants at the centers of galaxies containing billions of solar masses, will persist for timescales so vast they make the current age of the universe look like the first heartbeat of an infinite life. These gravitational monsters will slowly evaporate through a quantum mechanical process called Hawking radiation, losing mass particle by particle over eons that stretch beyond comprehension. The timescale for a supermassive black hole to fully evaporate is roughly 10 to the 100th power years, a 1 followed by 100 zeros, a number so incomprehensibly large that every metaphor fails before it. For comparison, the current age of the universe is approximately 10 to the 10th power years. The evaporation time of a supermassive black hole exceeds the current age of the universe by a factor so large you would need to write a 1 followed by 90 zeros. When the last black hole finally vanishes in a faint burst of particles and radiation, the universe will contain nothing but a diffuse cooling fog of photons and subatomic particles, spread across distances so immense that no two particles will ever interact again. Temperature everywhere will hover just barely above absolute zero, approaching it asymptotically but never quite reaching it. No structure will exist, no energy gradients will remain, no thermodynamic process of any kind will be possible. The universe will have reached maximum entropy, the state of perfect, irreversible disorder from which no recovery is possible. Time will continue, but nothing will mark its passage. Space will continue to expand, but nothing will notice. This is heat death, not a death by heat, but a death of heat. The final, permanent, irreversible end of all temperature differences, all useful energy, all possibility of work or change or complexity. The fire that once blazed across trillions of galaxies will have been diluted, degraded, and dissipated until it is indistinguishable from the cold it once fought against. The cosmos will not end in a dramatic explosion or a catastrophic collapse or a sudden, violent rupture of space itself. It will end in silence, in stillness, in a cold so absolute and so permanent that the word cold itself loses meaning, because cold implies the possibility of warmth, and warmth will no longer exist anywhere. But that future, terrifying as it is, lies trillions of years in the distance. What matters right now, what makes this story personal and immediate, is what the physics of heat in space means for the world you are sitting on at this very moment. Earth is warm. This is so obvious, so constant, so deeply woven into every second of your life that you have never once questioned it. You wake up warm, you walk through warm air, you feel warm sunlight on your face. Even on the coldest winter night, in the harshest conditions the planet can produce, The temperature rarely drops below -100 degrees Fahrenheit anywhere on the surface. Compared to the cosmos, that is practically tropical. Earth's most extreme cold is still 180 degrees warmer than the surface of the moon at night, and 350 degrees warmer than the cosmic baseline. Why? Why is this one small rock, orbiting one ordinary star, in one unremarkable spiral arm of one galaxy among 2 trillion, warm enough for liquid water, warm enough for complex chemistry, warm enough for life? The answer is not complicated, but it is fragile. Earth is warm because 3 conditions happen to be true simultaneously, and if any one of them were different, this planet would be as dead and cold as every other airless rock in the solar system. First, Earth orbits at the right distance from the Sun, close enough to receive approximately 1,361 watts of solar energy per square meter, far enough that the radiation does not strip away the atmosphere or boil the oceans. This habitable zone is narrow. Move Earth 15% closer to the Sun, and surface water would evaporate. Move it 15% farther away, and the oceans would freeze. The margin is thin. On the scale of the solar system, which stretches billions of miles from the Sun to the outer planets, Earth's safe zone is a sliver, a razor-thin ring of survivable distance in an otherwise hostile expanse of too much radiation or too little. Second, Earth has an atmosphere. Not just any atmosphere, but one that happens to contain greenhouse gases, carbon dioxide, water vapor, methane, in concentrations that trap just enough outgoing infrared radiation to raise the surface temperature by roughly 60 degrees Fahrenheit above what it would be on a bare, airless world at the same distance. Without this greenhouse effect, Earth's average surface temperature would be approximately 0 degrees Fahrenheit below the freezing point of water, and the planet would be a frozen, lifeless ball of ice reflecting sunlight back into the void. The atmosphere does not just distribute heat, it stores it. It holds on to thermal energy that would otherwise radiate away into space immediately after sunset, the way it does on every world without a meaningful atmosphere. The atmosphere is Earth's thermal blanket, and it is astonishingly thin. If you shrank Earth to the size of a basketball, the atmosphere would be thinner than a coat of varnish on its surface. That microscopic film of gas is the only thing standing between the warmth of our world and the cold of the universe. Third, Earth has oceans. Water has one of the highest heat capacities of any common substance, meaning it absorbs enormous amounts of thermal energy before its temperature changes significantly. The oceans act as a massive thermal reservoir, absorbing heat during the day and releasing it at night, absorbing heat during summer and releasing it during winter, moderating temperature swings that would otherwise make the planet uninhabitable. The Moon, at the same distance from the Sun, swings by over 500 degrees between day and night because it has no water and no air to buffer the transition. Earth swings by a few dozen degrees because the oceans and atmosphere work together to spread and store the Sun's energy across the entire planet. Remove any one of these 3 conditions and the warmth vanishes. Move Earth to the orbit of Mars and the oceans freeze solid within centuries. Strip away the atmosphere and the surface alternates between scorching sunlight and lethal darkness, with no transition and no mercy. Drain the oceans and daily temperature swings become hundreds of degrees, exactly as they are on every dry, airless body in the solar system. The warmth you experience every day of your life is not a given. It is not the default state of planetary existence. It is not what happens automatically when a rocky world forms near a star. It is a precarious balance maintained by a fragile combination of distance, chemistry, and liquid water that exists nowhere else in the known solar system and may be extraordinarily rare in the galaxy as a whole. Mars has an atmosphere, but it is over 100 times thinner than Earth's, too thin to trap meaningful heat. Venus has a thick atmosphere, but its runaway greenhouse effect has heated the surface to nearly 900 degrees Fahrenheit, enough to melt lead. Neither world demonstrates the gentle balance that makes Earth habitable. Both demonstrate how easily that balance fails. And this is where the emotional truth of the entire story lands. You are warm right now because you are sitting on one of the rarest objects in the cosmos, a rocky world at the right distance from a stable star, wrapped in a thin shell of gas that happens to contain the right molecules in the right concentrations, covered in liquid water that buffers and stores the energy of a sun that happens to be neither too large nor too small, neither too hot nor too cold, neither too young nor too old. You are warm because of an accident of chemistry and distance and physics that conspired, without intention or design, to create a pocket of thermal stability in a universe that is overwhelmingly, relentlessly, permanently cold. The stars did not make the universe warm. They made tiny, local, temporary pockets of warmth scattered across an abyss of cold, so vast that the pockets are invisible at cosmic scales. Each star heats the matter near it and nothing else. Each flame illuminates its immediate surroundings and leaves the rest in darkness. The photons stream outward at the speed of light and cross the void without warming it, because the void has nothing to warm. No atoms to absorb, no molecules to vibrate, no surfaces to intercept the energy and convert it to heat. The energy arrives at some distant grain or rock or planet and deposits itself, and for a moment that object is warm. But the space between the departure and the arrival, the billions of miles or light years of vacuum that the photon traversed, remains at 2.7 Kelvin, unchanged, untouched, indifferent. The void carries no trace of the photon's passage. The space between source and destination is as cold after the exchange as it was before. Human intuition was built to understand a world where heat fills rooms, where fire warms everything nearby, where warmth is ambient and pervasive and all-surrounding. That intuition works perfectly inside an atmosphere. It is worse than useless in the cosmos. The universe does not work like a room with a fireplace. It works like an infinite dark ocean with scattered matches floating on its surface, each match burning briefly, each one illuminating only the water immediately around it, each one surrounded on all sides by cold black water that stretches to the horizon in every direction. The matches burn. The ocean does not notice. This is what the title of this story really means. Why is space so cold when everything in it is burning? Because burning is not enough. Burning only heats matter, and matter is the rarest thing in the universe. The fire is real. The stars blaze. The energy flows, but it flows through a void that does not absorb it, does not store it, does not participate in the exchange. The void is transparent to heat. It lets energy pass through like light through glass, without keeping any for itself. And because the void is almost everything, and matter is almost nothing, the net thermal character of the universe is cold. Overwhelmingly, dominatingly, eternally cold. The fire does not lose. It simply does not matter at the scale of the cosmos. 1 trillion stars produce 1 trillion islands of warmth, and those islands are real and magnificent and capable of supporting life and consciousness and everything we value. But the space between those islands is so immense, so empty, so devoid of anything that could absorb the fire's energy, that the warmth never accumulates, it never builds. It never fills the room because there is no room. There are no walls. There is no ceiling. There is only the void, stretching in every direction for billions of light years, holding its ancient temperature of 2.7 Kelvin, with the patience of something that has been cold since the universe was 380,000 years old, and will remain cold until the last photon has been stretched to an infinite wavelength by the expansion of space itself. Imagine lighting a match in a cathedral so large it stretches beyond the horizon in every direction. The match burns. Its flame is real. Its heat is real. You can feel it on your fingertips. But the cathedral is so vast, so unfathomably cavernous, that the match does not change the temperature of the building by any measurable amount. The air a few feet from the match is already cold. The air at the far wall miles away does not know the match exists. Now remove the air from the cathedral entirely. Leave only vacuum between the match and the distant walls. The match still burns. The flame still produces radiation, but now even the space immediately beside the match is not warmed, because there is no air to absorb the heat. The photons from the flame travel outward at the speed of light and vanish into the distance, striking nothing, warming nothing, until they hit a wall so far away that the energy arriving per square meter is effectively zero. That is the universe. The match is a star. The cathedral is the cosmos. And the cathedral has no air. This is the correction. This is what the physics demands that you understand. You grew up believing that warmth is natural and cold requires explanation. That warmth is the default state of things, and cold is what happens when something goes wrong, when the heater breaks, when the fire goes out, when the sun sets. The opposite is true. Cold is the natural state of the universe. Cold is what exists when nothing interferes. Cold is the cosmic baseline, the starting point, the equilibrium toward which everything trends. Warmth requires explanation. Warmth requires a star, a nearby source of concentrated energy, the product of gravitational collapse and nuclear fusion in a cloud of hydrogen that happened to be dense enough to ignite. It requires matter to absorb that energy, matter close enough to the star that the inverse square law has not diluted the radiation to irrelevance. It requires an atmosphere or an ocean or a surface to convert electromagnetic radiation into thermal motion. Without all of these conditions being met simultaneously, there is only the baseline, the ancient hum, the 2.7 Kelvin whisper of a cosmos that was born in fire and has been cooling ever since. Your warmth is not the universe being generous. Your warmth is the universe making a rare temporary local exception to its fundamental character. We are the anomaly. Earth is the anomaly. Life, warmth, comfort, the sensation of sunlight on skin, the feeling of warm rain, the experience of a summer afternoon so perfectly heated that you forget the universe exists beyond the blue sky above you. All of these are the anomaly. The universe does not owe us warmth. It does not provide warmth as a default condition of existence. It provides cold, emptiness, silence, and darkness as defaults, and warmth only where the extraordinarily unlikely combination of distance, atmosphere, and liquid water happens to exist on a rocky surface orbiting a stable star in the brief window of cosmic time when stars still burn. We are warm by accident. We are warm temporarily. We are warm in a cosmos that is not, has never been, and will never be warm as a whole. The terrifying truth is not merely that space is cold. That is the headline, but it is not the story. The story is that the universe can be filled with more fire than the human mind can imagine. Trillions of stars burning at millions of degrees, flooding the cosmos with energy every second of every day for billions of years, and still leave the vast, silent, empty darkness between those fires completely untouched. Still leave the void at its primordial temperature. Still leave the overwhelming majority of the cosmos as cold and dark and empty as it was 380,000 years after the Big Bang, when the first photons broke free and the universe fell silent for the first time. We are warm because we are close to one small flame. That flame has roughly 5 billion years of fuel remaining. When it is gone, our corner of the universe will return to the baseline. The rock we stand on will cool. The atmosphere will dissipate or freeze onto the surface. The oceans will boil away first, as the sun swells into its red giant phase. And then, after the giant has shed its outer layers and left behind only a white dwarf, the remaining material will slowly freeze as the dying ember provides less and less heat with each passing billion years. Everything that made Earth warm and alive and extraordinary will fade, and the cold that was always there, that was always the default, that was always pressing against the thin membrane of our atmosphere from every direction, will reclaim this place, as it reclaims all places, as it reclaimed Mars when its atmosphere thinned, as it will reclaim every planet around every star that eventually burns out. The cold does not conquer, it simply waits. It is the original condition, and warmth is the temporary interruption. The universe is full of fire, and the universe is cold. Both of these statements are true, and the distance between them is the most unsettling truth in all of physics. The fire burns in its tiny pockets, glorious and temporary, and utterly insufficient to change the character of the whole. The cold stretches between them forever, not as an enemy of the fire, but as the background against which the fire briefly appears. And we exist here, on this one warm rock, orbiting this one ordinary star, wrapped in this one thin atmosphere, for this one brief moment in the long, cold history of a cosmos that was never built to keep us warm. Step outside your atmosphere, and the universe does not care that you are alive. It does not resist your warmth or attack you with cold. It simply has nothing to offer you. No air to breathe, no medium to carry heat to your skin, no buffer between the blazing radiation of the nearest star and the infinite emptiness between the stars. You are on your own, carrying your warmth with you, a self-contained island of thermal energy drifting through a void that has no use for you. And the void through which you travel, the void that constitutes almost everything that exists, will remain exactly as cold after you pass through it as it was before you arrived. Your presence does not register. Your heat does not linger. You do not warm the cosmos by existing in it. This is what the universe has been trying to teach us since the first human looked up at the night sky and felt the cold air of a winter evening on their face. The cold you felt was not the exception. It was the rule. The warmth of the fire behind you was the exception. The stars above you were tiny fires in an infinite dark, each one warming only the matter closest to it, each one surrounded on all sides by a void that their light would cross, but never warm. The universe is full of fire and yet dominated by cold, and nothing that burns, no matter how bright, no matter how hot, no matter how long, can change that. Because the cold is not the absence of fire. The cold is the nature of the void, and the void is almost everything there is. The fire burns, the void endures, and the distance between them is the temperature of reality.